Hello, my name is Wojciech Mrozik, and I'm Faraday Institution Senior Research Fellow at Newcastle University, United Kingdom. And during this presentation, I'll discuss our preliminary work on possible ways to extinguish lithium-ion battery fires. Before I head straight to the result, it is important that I set a context for our work. I'm not going to discuss exactly what is, how it's built, lithium-ion battery fire, and why it catch fire, and what is a thermal runaway and a vapor cloud. There is a ton of literature that discuss the matter, including, for example, publications from our group. What I want to highlight is that any abuse of the battery leads to thermal runaway, and depending on the circumstances, it may obviously result in a vapor cloud formation, which is toxic and potentially explosive, fire, or explosion. And there is influence of some factors, for example, chemistry, so NMC versus LFP, or state of charge, which may change the outcome of the thermal runaway. We are fully aware of limitation of our work, such there were no repetitions, we tested only single type of chemistry and only one form factor, and also that we have a specific setup for our work. Though it's quite likely that with a different setup and chemistry, the outcome of those extinguishing agent may be a bit different. Therefore, please treat this presentation as an indication and a framework for future experimental work. So those results are basically mostly informative at this point. Okay, let's go straight into the meat. So we run our tests in County Durham and Darlington Fire and Rescue Service Training Center, which is located in Northeast England in March 2022. This facility possessed full extraction and treatment system, so we were able to run our experiment without concerns about affecting the neighborhoods. And you can see the map and the aerial view of the facility. In our experiments, we used Envision SAC modules, the ones you can find, for instance, in Nissan Leaf 2 electric vehicle. The module consists of 8 NMC pouch cells. They are wired into 4 pairs, and on the left you can see some specification of the module. So we took 5 of those modules and created energy storage system that basically mimic the domestic one, and the capacity is roughly 8 kilowatt hours, so it's rather on the lower end of battery energy storage system. Modules were mounted into open framed metal case, basically to direct the flames, just only they're going in one direction, and you have better access for extinguishing agent. All of the modules were at 100% state of charge, and to simulate the failure, we overcharged one pair of the cells in the second from the bottom module, as you can see on the picture. Let's say that the rule is that the firefighters should be at the scene in roughly 15 minutes. But during our initial testing, when we left the system to burn without any intervention, it was gone in just 7 minutes. So in case of our experiments, we let the fire go for roughly 1 minute before deploying the agent. Also on this slide, you can see how the thermocouples were placed in our system. In our experiments, we wanted to check how portable system, handheld extinguishers, or other methods that are used, for instance, by firefighters, perform against our burning system. So we used cold cut cobra, which is widely distributed among various FRS. And this is basically a water lance with a high pressure, roughly 300 bars, that can cut through steel or concrete. Liquid nitrogen, well, as you can see, it's not exactly portable on the middle photo. But from the scientific literature, what we know that liquid nitrogen can stop thermal runaway, for example, in a single cell. And we also heard that there are some ideas to use such system in battery energy storage systems or something similar. Thus, we wanted to give it a try. So we had a 200-liter tank with a 2-meter length. But in this case, we use it only for one module, as we had some safety concern, which I'll discuss later. Next one was F500 encapsulator agent. It's basically a 5% surfactant solution in water, which is widely used for other types of fire. And AVD, which is an aqueous dispersion of chemically exfoliated vermiculite. And we use it only for single module because we faced some technical difficulties during the 5-stack experiments, so we are not showing those results. As mentioned previously, we let the stack burning for 1 minute before deploying the agent, and for single module, we apply the agent as soon as possible after the fire started. On this slide, I just briefly present what the experimental site looked like, and in the first top photo, you can see the chamber. Basically, it's a shipping container with fitted ventilation and extraction system on top. The middle photo shows the test article for the site, the point from where firefighters was attacking the fire. So basically, that was the view from firefighter perspective. And the last photo is, let's say, en-face view with all the wiring visible and an open door behind and on the side of the system. Those crude sketches show roughly where the gas sensors and cameras were fitted inside the container. Okay, let's go to the most interesting part, and we start with cold cut cobra. The left video shows the initiation of the fire by overcharge. And you can see there is the gas The second video, which is a view from above the energy storage system, shows the actual cold cut cobra attack burning system. So cobra inside the system because it's a quite narrow water stream, the operator has to adjust the point of attack. On the graph on the left, you can see the voltage of overcharged cells, the rise and then sudden drop that indicates thermal runaway and fire starting. And the thermocouples indicate the temperature we reach during various experiments. Just bear in mind those colors are not corresponding to ones on this graph. So as you can see, the highest temperature we had for TC1 and later for TC2. And the rest of the TC show some elevation, but usually below 18 degrees Celsius. So what happened during this experiment? We lost the module number 2, which was put to overcharge, and applying cold cut cobra did not stop fire propagation from cell to cell within this module. We also lost module number 1, the one at the bottom, and it was due to the adjustment of the cold cut cobra during operation, as the operator angled lance a few times and he accidentally cut through the bottom module, leading it to a thermal runaway. Interestingly, we don't see much fire later from the cells, and even though some of them were in the thermal runaway, producing only a vapor cloud, which you can see at the end of the video on the previous slide. We also monitored the remaining cells for more than 1 hour after the event to check if they would go to thermal runaway, and they were okay. So we saved modules number 3, 4, and 5, so 3 out of 5. And after this time, we haven't noticed any temperature rise, and then we set it on fire by the burner. Okay, now F500 agent. In this experiment, we had 6 9-liter extinguishers. Effectively, we used 4 to tackle the incident. So again, fire, and soon you'll see the firefighter approach. What is interesting here, you could see that the flame is gone in just a few seconds, but there is still production of vapor cloud, suggesting that the cells subsequently go to thermal runaway. Well, this violet gas is the vapor cloud, and we know from our previous work that this topic is potentially explosive, and the big problem is that it can be mistaken as steam. So you can see how much is produced, and imagine this happening in not so well ventilated space as expected. Again, you can hear and see right now that another cell is going to run away. You can see now clear distinction between previous cloud, vapor cloud, which was dense, thick, a little bit blackish, and now steam from the extinguisher. Roughly at this point we already stopped thermal runaway going, just using remaining extinguishers to do the job. So on the graph, you can see the voltage drop for module 2 first and later for module 1, and TC1 and TC2 basically reflect that situation. So here and here. So interestingly, TC5 showed elevated temperature at some point at the beginning. It's probably due to the flame going up and under over the system where the thermocouple was fitted. So nonetheless, we stopped thermal propagation to module 3 to 5. So again, we were able to save 3 modules out of 5. And the indication burner is the time when we set again the system on fire. So as you can see, we were monitoring this system for some time, and later we used the burner to burn remaining modules. Okay, now liquid nitrogen. Here there is only one module in the case, as you can see. We wanted to check if we can stop thermal propagation from cell to cell within our module, just one. So we applied liquid nitrogen as soon as possible after the fire started. So liquid nitrogen leaving the lens is in the form of gas, but still is roughly minus 190 degrees Celsius. So it should have a high cooling capabilities. You could see there was a very quick knockout of flames. It didn't resurface. But there is also a high volume of gas, which is a mixture basically of liquid nitrogen and a vapor cloud. I speed up a little bit. Good. You can hear and see now that another cell is going. Having only one module, we were monitoring the voltages of cells from each pair, so 4 in total. We also had 3 thermocouples. One was sitting on top of the module, one was at the bottom, and the last one was put, let's say, into the middle of the module, like slit into the side of the module. As you can see, liquid nitrogen didn't stop the thermal propagation within the module, although it knocked out the flames very quickly. Another effect you can see on this graph, it is liquid nitrogen lowered the temperature of flames, of thermal runaway, let's say, from roughly 900 previously down to 500 degrees Celsius. And nonetheless, all the cells were dead after some time. Okay, and finally, AVD against a single module. Again, a single module, and we had a 9-liter portable extinguisher to deal with the fire. What can you see here is the application of the agent should be better, so it should be directed more towards the module as long as possible, not all over the place. Also, AVD should create a shell-like structure around the module to prevent fire going. You can see it's a quite dense dispersion. They definitely should be better applied, which highlights the importance to train and inform the users of those systems how to effectively apply it. Yeah, just another cell went into the thermal runaway fire. The extinguisher had no effect on our single module, but that is no surprise when you compare it to previous agents. Every time we applied any of those agents, we lost a module or sometimes two. So taking into account how this module is built, it's very, very, very hard and tricky to stop thermal propagation within the module. Also, as I mentioned, the application should be better. You should be straight onto the module all the time, not, let's say, all around the place. And finally, just a brief discussion about gas analysis we made during this work. Our detectors monitored hydrogen, hydrogen cyanide, hydrogen fluoride, nitrogen dioxide, sulfur dioxide, and carbon monoxide. And although our system was ventilated, you could see large volumes of a vapor cloud and few points almost in every video. So imagine it is happening in a closed space or less ventilated spaces. In various moments, we exceeded immediate danger to life and health for HF. This limit is 30 ppm for a minute or even longer. And we also had elevated levels for carbon monoxide, so way above 2000 ppms. According to our previous studies and science, we know that if NMC battery is above 50% state of charge, thermal runaway results in jet-like flames. And that was visible at the beginning of our experiments, as you can recall. With flame, usually there are lower concentrations of monitored gases. However, in our case, we have eliminated flame, but the thermal runaway was still going. So basically what happened was that we traded one hazard, fire, for another one, toxic and flammable vapor cloud. And that is another interesting puzzle to resolve in a field of thermal runaway and fire of lithium-ion batteries. So what are the implications? That, for example, we must review or come up with standards, regulations that will consider both fire and vapor cloud risks. A quick solution could be, for example, fitting VOCs detectors in or near the energy storage system that could warn if the system is still in thermal runaway. For instance, when the firefighting agent was applied within the system and if it's safe to approach. Some more conclusions. Well, now we have even more questions than answers, to be honest. But just to remind you that we are aware of our limitations in these studies and that we tested only a few portable systems, and they are on the market solutions that are aimed more towards stationary applications with sprinklers, tanks, and so on and so on. What we learned is that often you will have to stop thermal propagation from module to module rather from cell to cell. It will be obviously more of protecting the surroundings and limiting the fire spread than stopping it right on the spot, well, until we will progress with our knowledge and solutions. Of course, there is a strong influence of the battery form factor and how the system is built. So cylindrical cells usually, where in the module they have more space among them. So other systems will be either module free, meaning that the whole pack will be just one big modules. Anyway, it will be all limited to the possible access of firefighting agents to the system. And it will be different, for example, for electric vehicle and different for energy storage systems. Obviously, we will be doing more tests, and that includes repetitions using different form factors. So for example, we'll have a comparison between cylindrical pouch and prismatic cells. how the cells are embedded into the system. So basically, is it a number of modules, or is it one big case? And use of a different firefighting agent, and water mist could be quite interesting one. Finally, I would like to thank my colleagues who are involved in the preparation and the running of these experiments. Without you guys, it wouldn't be possible. So great job. Big kudos to Country Durham and Darlington Fire and Rescue Service for letting us use the facility and for the friendly and helpful crew. A massive thanks to UK Fire Association that funded this work. Big thanks to SAVAT and RELIP, Faraday Institution projects. We obviously are part of them. Draeger for helping with gas sensors, and finally companies that agreed to take part in those tests. So thank you very much you for your help and collaboration. And thank you for your attention.